we treat golf balls, golf clubs, baseball bats, pantyhose. We've even treated habanero peppers, which is 100 times hotter than a jalapeno, because it improves the cracking ability, and it's a much more uniform shape after it's been cracked as opposed to cutting. Golf balls will go farther. Of course, that makes them illegal in tournament, but you can use them on the weekend with your friends. The golf clubs that we treat, they say that it enlarges the size of the sweet spot. Baseball bats are pretty amazing. We've had umpires actually take bats away from some of our players, cut them in half, thinking they're corked, to have to go buy a new bat, which is promptly brought in to be retreated. Cool Note will treat all types of brass musical instruments, everything from trumpets and trombones to tubas. We've done everything you can think of. The way that we improve the material through deep cryogenic tempering is by taking it to 300 below, is going to refine the grain structure. We're going to complete what is called a martensitic transformation. We also get a better molecular bonding, and we improve all of the wear characteristics. The computer program is really very simple to operate. We double-click on an icon, and the computer takes over and follows a profile from there. The profile will take it down gradually to 300 degrees below zero, and it'll hold it for a predetermined amount of time, approximately 24 hours, before it brings it back to room temperature or ambient temperature. At that point, it's removed from the deep cryogenic processor, and we do a post-temper in an oven to about 300 degrees above. There is also, during the tempering phase after the cryogenics, a carbide precipitate growth will fill the microvoids. What this means is that the material itself is going to be able to be more resistant to wear and abrasion and will last longer. So drill bits, cutter blades, punches will last 3 to 4 times longer.
See, here are some aluminum pistons. These actually are a series of pistons that just happen to be here today for one of the famous racing teams. I can't tell you which one because almost everything we do is under secrecy agreements. One of the problems with racing components is as the racing engines heat up, they tend to get elliptical and lose their shape because of the residual stresses in it. We'll remove those residual stresses, and once they're removed, and this is machine true, then this thing will keep its dimensional stability.
So there is less blow-by, higher compression, and you get higher horsepower. And the engine itself runs stronger and will last longer. We utilize liquid nitrogen in our deep cryogenic processor because liquid nitrogen boils at a minus 323 degrees Fahrenheit. That's to mean that it is a liquid anywhere below that temperature. We flash that to a gas and use that in our deep cryogenic processor to treat parts to minus 300. It's a cheap, efficient gas to use, and it's a green system. The liquid nitrogen that we use in our process, and I said it'll boil at a minus 323 degrees Fahrenheit. That is, it is a liquid below that, and it flashes to a gas at a minus 323. Water, on the other hand, turns to a gas at a positive 212 degrees Fahrenheit. That's a difference of about 500 degrees. So if you were to take liquid nitrogen and you were to pour it onto the floor, that's similar to taking water and pouring it onto a hot plate. It will, in essence, boil on the floor. In Celsius, it's about a minus 190 that the liquid nitrogen will flash to a gas, and water turns to a vapor at a positive 100. That's a difference of about 300 degrees in Celsius.
What I'd like to show you now is what happens to a gas as it's cooled. This balloon is full of gas. We've just blown it up. It's at room temperature, and it's defined the stretch to the rubber in the balloon. As we place it in the liquid nitrogen, the air inside becomes much colder. As you can see, the balloon's becoming smaller and smaller. And I have to handle it gently at this point because I can break the rubber because now it's become embrittled. You can hear the embrittlement of it. It's completely deflated, and as I place it on the table and it's exposed to room temperature, you're going to see how fast the air can recuperate and expand. If this were a metal container that had a sealed lid, it would actually collapse the can flat, actually ruin it. At this point, the balloon, it's still hard on the bottom because it couldn't thermal exchange. You can see the pattern developed by the cold still. It's just about to come back to room temperature, where it'll operate exactly as it did before we froze it. And it's fully malleable again, with no ill effects. Now you've seen what it's done with the balloon. Let's move on to a couple other items I think you might have some interest in. Okay, now I'm going to take an apple straight off the shelf. Very delicious, by the way. And we're going to place it within the medium. You're going to see a lot more boiling take place with this apple than we did with the balloon because of the mass involved. The boiling, again, is caused by the apple being 400 degrees hotter than the liquid nitrogen. Okay, I believe the apple's ready for our test. Follow me over and we'll see what happens. Okay, let's find out if it's going to bounce or break. But I want to show you how something very soft and very delicate can also become very hard by freezing it to close to absolute zero. We're going to immerse them. And again, we get a lot of boiling. That's expected. This flour was 400 degrees warmer than the liquid nitrogen in this pan. Okay, and I believe that we're fully unbrittled at this point. So what I'm going to do is pull them out, and we'll see what they do on the table. Now, if you'll watch closely, we've powdered our mum.
The future is boundless. We have barely scratched the surface. We have markets out there we haven't even had a chance to touch yet, and they're all exciting. The world's the limit.